Yeah. Because you're totally excited about your grade right now?
Yeah.
Is it over 100% because you've got the 2 points that I put in, right? So it's like done, right? I will totally finalize the grades right now if you promise to maintain that performance.
Okay.
How does that sound? Let's do it. I mean, I can't tell you like how much it would make my life if I could give an entire class an A on even one exam, like have the whole class get an A. Like if somebody would ever like call me out on that and like just never happens. Never happens.
Don't tell us that.
You know.
Now you're gonna scare us.
Well, I mean, I'd love it. I would love it. I think it's totes doable. It's just a question like you got to have everybody ready on that day. And it's so like hard with a group of this size to have everybody fully 100% on their game prepared, right? Yeah. So hard. So actually, as you all are getting settled, and I know still working maybe to find your groups, I just want to talk for a minute about the 2 optional parts of the class. Remember that I have put forth an option to replace your low exam score if you do one of 2 things. One, you can join the book discussion on the book called Fevered that you'll probably want to hop on Amazon, get for your Kindle or something. And if you read and partake in that discussion, which by the way, I would like to get the first discussion finished by the time we take the first exam, if possible. So we should get that kicked off, sooner better than later. So that is one option for replacing your low exam score, is if you're in that Fevered discussion, you're participating like crazy. I like to see an original post and interaction with other students. That is something that shows me that you've really been engaging in the reading, and then also some nice interaction with your fellow group members that are in there discussing as well. So I'll probably put forward a rubric, actually, that we can put on that that'll kind of show you how I'm looking to assess you on that. So that's one way you can replace your low exam score. The second way is if you really like textbooks, you can buy the textbook, the Connect software, get the ebook, and engage in the Learn Smart activities. And if you submit all those Learn Smart activities as they come, that is a second way to replace your low exam score. Now, one caveat, you may not replace 2 low exam scores. So if you want to do both activities, like you want to engage in Fevered and you want to do the Connect stuff, you're still only going to be able to replace 1 low exam score. But those options are definitely out there. Okay, Sarah was up first, and then I'll get you, Julia. Yeah.
Are those due dates that are on the Connect that it's like slowly starting to come up? Are those
Yeah.
going to be the due date?
Yeah, I'd like them to be, but I'm also fairly flexible. So if you guys feel those due dates are coming too fast, or you'd like a little extension on, just holler at me and I will modify them. So I'm not too picky, but I'm kind of trying to base those on what our coverage is in lecture, just so that they correspond pretty well with what we're doing in lecture. Yeah.
My question was that pretest that you said we could take.
Yeah.
Was that optional, and that could replace the 5 points for a low homework score as well?
Okay, so just to differentiate, the other thing that's out there is one that you're seeing on the announcements today, and that is if you get in and do that pre-test and knowledge survey, that is what will enable you to get rid of your low homework score rather than your low exam score. So this is a little bit different, right? This is actually something that will help you with your homework rather than the exam. Andre? Yeah, that's a great question. So he's wondering if I'm reading everybody's knowledge surveys. Those will eventually be assessed and graded, but not linked to you for purposes of just learning assessment. Yeah, so kind of is sort of the answer to that question. Any other confusions? Because I know as we're getting into things, you're starting to figure out what parts of the course are optional, what parts are not. Because I'm kind of tricky that way. I get a lot of different options out there. Yeah. Yeah, Fevered is split into 3 discussions, 1 per exam, basically, or exam period is kind of the way I look at it. And the cool thing about that is that come the end of exam 3, we'll finish right around then, we'll finish our book discussion, and that'll easily allow me to then go back and replace your low exam score for you. So, yeah. And if we feel like our discussion's just running too well, we want to leave it open for a little longer than the first exam, we'll do that, and that's fine. But it'll be roughly in those increments, roughly, yeah. Yes, they are. And so if you guys get a chance, you think you're going to like the fever book, get into modules, and notice that there's a module dedicated to fever. And you'll notice I've opened discussion 1 already, and have mentioned that for that one, we're reading the introduction in chapter 1, and that's it. So that's all we're discussing right now. Yeah, Amy. Yeah, no, the take-home final's off limits. It's you all got to do the take-home final. You're all gonna love the take-home final anyway, so you wouldn't want to get rid of that one. Okay, good. Thank you. Please keep this conversation coming. I want to make sure that we're all communicating with one another all the time, and letting me know if there's anything that confuses you or any aspect that you're just a little uncertain on. Let me know, because I definitely want to hear your voices. And anytime during lecture, anytime that you want to pipe up with something that comes to mind, your voices are always welcome. A few more announcements other than what we already talked about. One regards lab tomorrow. Remember that lab tomorrow will be the first of 4 labs where we're basically flipping it, which I'm not sure if that's quite the right term. Maybe somebody can help me come up with a more creative term. But basically what it means is that you will get ready for lab completely outside of lab. So when we get to lab tomorrow, I'm hoping that more or less you'll be ready to hit the ground running. We will do a quick kind of demo where we'll do the negative strain together. But then otherwise, I'm going to assume that you know what is going to happen in lab tomorrow, and you're all ready to go with what we'll be doing, including the lecture material, which is under vodcast in your lab shell. So don't look for it in lecture, look for it in lab, and you'll find that lab 2 vodcast. Who's already watched it? A few people? Nice, good. I think it's, 20 minutes long, so not real long. But what'll be nice about that is that we won't have to worry about covering background in lab. And later in the semester, I'll probably survey you and see how you like that, and see if you like that better than having me yammer at you or your TA yammer at you before the lab starts. Okay. Cool. That is one thing, and then I guess there's just a couple other things up here regarding your group work. If you guys could try to determine a topic and send that my way by the 17th, that would be great. Really like to begin to solidify a topic, but I also love when you just bounce off of me with ideas. I've definitely gotten some groups that have emailed me with 2 very disparate ideas and they're not sure of where they're going. I can sometimes give you feedback on one topic or another regarding whether it will be more current, whether I think you'll be able to find more literature on one or another, or sometimes I can just give you search terms. Like one group wanted to do something on, how they sent me something like, how certain people don't get HIV? We'd like to do something on that. And I can say, oh, well, that's when they're doubly deficient in CCR5. So now you have a search term, right? You can actually go and look for that topic. So that is a way in which I can be helpful in guiding you as you solidify what it is that you're doing with that. Homework 2 is now up. That'll be due on Tuesday, just as is always going to be true. So we'll always either have a homework or we'll have an exam on Tuesdays. And I think we've gotten that down pretty well. It looked like everybody did pretty darn well on the first homework. I'm about halfway through grading it. So I hope to finish grading the rest of you. If I haven't graded yours yet, I'll be doing that soon. I'm kind of trying to give you feedback on it, and you probably will get a little email that says that I've given you a note and finished up your grade on that homework. So the other thing is that I was really impressed with the extra credit. I gave everybody 2 points of extra credit for being in class basically and turning in that survey or the little true-false test. And I just wanted to mention that there were only 10 people not in class that day, which is rocking. So I'm super jazzed. I'm super jazzed about that. Okay, let's hop in today and finish our macromolecule game. We need to talk about carbohydrates, but first we need to review a little bit about proteins, because right at the end of last hour, you guys were really getting stoked on the personalities of the amino acids, and you were determining which of them liked water, which of them hated water, which of them were acids and bases. And so now I want to apply that within the context of an actual real protein. And maybe some of you have found your way to the protein database and you've actually looked at some of the ribbon diagrams of proteins in there that you can rotate through 3D space. This is one of those ribbon diagrams. So you can see here that this particular protein, which is an L-arabinose binding protein, meaning it's a protein that binds to a sugar. So notice that this particular protein has what kind of secondary structures? Do you see some recognizable secondary structures in there? Beta sheet and alpha helix, right? It has both. Actually, the alpha helices are really visible. So I want to draw your attention to one of these alpha helices, this one right here, the blue one. And I want you to notice that region B I'm trying to show is a region that faces the protein interior, cowering away from the aqueous exterior. Region A, however, is facing that aqueous environment. And the question, the first review question I have for you is in which region, region A or region B, would you find the amino acid glutamate? Glutamate. So discuss it really quick, get yourselves activated back to amino acids, personalities. How do we answer this question? How do we know where glutamate would be? So folks in this area are remembering that glutamate is what kind of amino acid? Acidic. So meaning that it has what kind of charge? Negative. Good. So then meaning that it what? How does it feel about water, glutamate? Oh yeah, that negative charge really likes to cuddle with the partial positive charges on water, right? So where would we find it? Which region? Okay, good. We would find it facing the aqueous environment, cuddling with water, because it likes water. It is very highly hydrophilic. Excellent job. We call this kind of helix an amphipathic alpha helix. Amphi actually means dual personality, right? A split personality. This helix has one side that loves water and one side that hates water. Right? We know people that are got that split personality. This helix has that split personality. So whenever you think amphi means dual nature. Amphipathic alpha helix. So we see some of the amino acids facing the exterior, some of the interior, and making this overall amphipathic. But notice that in that picture of the protein, we also saw some really interesting, unique areas that were neither beta or alpha. We saw some areas where we had a quick turn and then maybe another alpha helix. So there's a particular amino acid that tends to induce kinks. What is this kinky amino acid? Proline. Proline, my second favorite amino acid, the kinky one that induces, right, that induces the direction changes. Let's look at why proline is kinky. Recognize that it is the only amino acid whose R group binds back again to the conserved nitrogen there. It's the only one that binds twice to the region that's conserved in all amino acids. So it kinks back up on itself. And because of that, in any place that it is found, it is going to put a kink in the works. So do you think that it would like to be in the nice swooping turns of an alpha helix? No, because it's going to kink them. And that's no good. It's not going to allow the nice swooping turns. So it is called a helix breaker, and it is kinky. So proline is found in turns and direction changes. We now are completely done with proteins, and we're able to jump into the next class of macromolecules, carbohydrates. And let's start from the very beginning. So I want you to discuss with your group the functions of carbohydrates. Okay? So list 2 functions of carbs. Holler at me when you've got them. Oh, already ready. Doug is hoping to hold on to that current grade that he has with the extra credit, over 100%, right? Okay, what you got? Energy storage. You bet, good. So glucose is one of those quintessential carbs. We know glucose is a quick source of energy. So energy source and energy storage might be the first thing we think of with carbs. Unlike proteins, they are the preferred source of energy in the cell. Okay, good. What else do carbs do? Say it again. Oh, that's fine. Go ahead. Structure, yeah, absolutely. They can be structural molecules as well. And in fact, we're going to see that in the cell wall of bacteria, they provide a certain amount of rigidity to that cell wall. So unique kinds of carbs in that kind of role, a structural role. What else? Anything else? Yeah, Bridger.
They can be identifiers.
Yeah, so molecules that allow for recognition of cell surfaces. And in many cases, that would, say, be a glycoprotein or glycolipid, where you had in a cell membrane, you had a little carb moiety that sticks up from that membrane off of a protein or off of a lipid that is some sort of identifier, right? Good, that's excellent. Let's go ahead and see what I've got in my list and see how you guys did. Energy source, energy storage, first ones you guys came up with. Components of cell walls, we got there with our idea of structural molecules. Recognition and signaling, I think we got there too. And maybe the only one that we didn't get to is the fact that, in fact, carbohydrates, monosaccharides, are actually found in nucleic acids. Right, review real quick. Nucleic acids are what? DNA and RNA. So what kind of sugar is found in DNA and RNA? Ribose, right, the ribose sugar, the 5-carbon ribose sugar. So we find them in those molecules as well as in cofactors. In fact, you guys may not think about it much, but guess what? ATP has a sugar in it, a monosaccharide in it, okay? So let's ask our next question. You brought up the fact that glucose is a quintessential carbohydrate. This is a picture of glucose. However, this glucose molecule may not look like you think it should look. In fact, it's rarely drawn in this way. So take a moment and tell me, how is it usually drawn? How do you usually think you see it depicted? Yeah. Oh, I love it. I love it. We're getting more than one right answer here. Okay, so who's got one? Yeah, Lauren. In a ring, right. So more often than not, we see this drawn in its ring conformation. That is to say that this oxygen right here typically attacks the carbonyl carbon of this aldehydic group. Okay, that's a lot of chem lingo to simply say that this forms a ring in which the oxygen is a constituent of the ring. I want to show you some pictures of the ring. And notice that the oxygen in fluorescent Barbie pink now has been incorporated into the ring. Notice that it becomes the 6th position of the ring. So one of the things that I want you to be a little familiar with is the carbon numbering system as we go from linear to a cyclic form of the sugar. So I'm just going to draw your attention to that while I have Seth say what he said. He didn't call this a ring, he called it a chair. A chair is the conformation. So notice that this is carbon 1, 2, 3, 4, 5. And notice that the oxygen on carbon 5 is what does the attacking and becomes a constituent of the ring. So how would we number the carbons now in the ring? Where is carbon 1? Far right, far left, bottom what? Top, right here? This one? Okay, the one guess is that it's this one, carbon 1 there. Oh, not that one? Which one? Far right, right? Okay, backwards. So this actually is carbon 6. So notice that carbon 6, when oxygen attacks here, carbon 6 gets left out. It is the lonely carbon that doesn't get to be part of the ring, right? So it gets left out. So in fact, carbon 1 is here. 2, 3, 4, 5, and then 6, as I said, left outside of the ring. This is actually important because, as it turns out, just in the same way that amino acids were the monomers of the polymer, monosaccharides are the monomers of the polymer. So what would we call the polymer in this case? Polysaccharides, right, good. So just to come back really quickly to Seth's answer of this being a chair, what that indicates is the stereochemistry here and the way that the ring actually forms what looks kind of like a Barco lounger chair formation. And that is absolutely right. That's absolutely right. And this Haworth projection is kind of showing that. Don't worry if you don't know a lot of the stereochemistry on this. All I want you guys to know is that it tends to form a ring. And I want you to know how to number the carbons on that ring. But I also want you to come back to what I said was the big take-home message last time. What was that big take-home message? Yeah, do it. Good, Julie. Like? Like does something like dissolves like. Oh, so, hey, look at this sugar and tell me, based on, look at all of those OHs on this puppy, how does it feel about water? It loves it, right? Because you've got all these polar OH bonds in the sugar, and they're all about cuddling with the polar OH bonds in water. So there's a lot of like dissolving like going on. Now, of course, you could also remember that if you took some sugar and mixed it into some water, it would dissolve, right? So we know that this is a very hydrophilic or water-loving molecule. Excellent job. So you guys mentioned that if we take one monosaccharide and we bind it to a second monosaccharide, and Alex will probably tell us what molecule is lost. Water. You got it. Absolutely. So we've got our little balls being lost one more time here as we form a glycosidic linkage. So the linkage that holds one monosaccharide to a second monosaccharide is a glycosidic linkage. And that's what you're seeing in this particular molecule called a what? Two monosaccharides or a disaccharide, right? So a glycosidic linkage linking together two glucose molecules. So then my question becomes to you, lactose, the disaccharide in blank, another disaccharide, not maltose, but a different one, is composed of one galactose and one glucose. So two different kinds of monosaccharides. Well, I guess glucose is the same as what we see in maltose. And then sucrose, another disaccharide. These disaccharides are some famous molecules, or blank, is made up of one glucose and one fructose. What is our answer there? I kind of like D, coconut. No, yeah, you're absolutely right. Lactose is the disaccharide in milk. And this is going to come up later, right, where we're going to be talking about bacteria that like to ferment lactose. That is the lactic acid bacteria. They live in milk, they ferment it from lactose into lactic acid, and they make things like yogurt and sour cream, right? So they like to eat that particular disaccharide. No, now we add another one of these on here, we get a trisaccharide and so on forth, and finally we get a polysaccharide, right? And this is a small region zoomed in on one of our favorite polysaccharides. This particular polysaccharide is glycogen. Does that sound familiar to anybody? Oh, it does to Justin, right? Because glycogen is so important to athletes, right? Because, what is it? It is our energy store, right? It is what we tap into when we're like, thank God for my liver that stores so dang much glycogen and allows me to tap into so much energy, right? This is what I do when I'm doing triathlons. I'm like, go liver, trying to give me more energy. And we know that this molecule is packed with power. In fact, we can get very, very large, very, very long polymers of glucose all linked together by glycosidic linkages. However, some of you who are nutrition-oriented will tell me that glycogen by no means is the only polysaccharide of glucose. One glucose after another, we get some other polysaccharides. For example, nutrition folks. Oh, who was a nutrition folk? Oh, it's Erin. She's gone. Erin. Oh, yeah, that's right. She has another class she has to go to. So how about starches like amylose and amylopectin? Other polymers of glucose that we eat in our diet, right? We like to take those in, do a little carb loading, and we know that those are also important glucose polymers. Now, some other folks are going to say, yeah, there's another super important glucose polymer, and this glucose polymer is cellulose. So I know that Matt, right, Matt C., you're like our egg guy, and there's some others who are out there. Where are you? Dang it. So who else is egg? Ellie, are you? No? What? Kind of egg? Horse stuff. Yeah. Yeah, Greer. Yeah, absolutely. So tell us then about why it is that ruminants, right, can eat cellulose. Like they chow down on grass and cellulose-containing molecules. Or if you think about a goat, right? I had a great friend goat at one of the campgrounds that I stayed at one point bike touring, and it was trying to eat my t-shirt, right? And so why is it that they can eat cellulose and we can't? What's going on there? Cellulose is just a polymer of glucose. All cellulose is one glucose linked to the next, linked to the next, linked to the, hey Aaron. And so we see what is the difference there. Why can ruminants, cows, and caribou and buffalo, why can they chow down on cellulose and we can't? Do you know? What's going on in their gut? Yeah, hit us. Yeah, you bet. So ruminants have a symbiotic relationship with bacteria, and not just bacteria, but also fungus and protists. They have a rumen packed full of microorganisms that do the work for them. So as it turns out, cows aren't actually degrading cellulose. Their bacteria in their rumen are. And in fact, we could think of the rumen as being something like a 40-gallon fermentation vat in which a ton of gas is being produced. And chewing of the cud, right, is an efficient method to regurgitate some of that material that's been partially digested and then redigest even more of it. Very efficient metabolism. So we could think of cattle and buffalo and sheep and caribou as being what we term foregut fermenters, and it's the relationship with the bacteria that they have that allows them to eat the cellulose. So as it turns out, although cellulose and glycogen and amylopectin and amylose are all polymers of glucose, in cellulose the bonds between the monosaccharides are slightly different. They're called beta instead of alpha, not important, but they're slightly different, and so we can't break them. But bacteria can. Bacteria of the rumen can. But then I know that some of you are into other kinds of animals rather than maybe your typical agricultural animals, and might be enjoying to see that sloths. Has anybody ever been to Costa Rica and seen? Yeah, isn't that rad? So this is a three-toed sloth, and this three-toed sloth eats leaves. And so it has a symbiotic relationship as well with bacteria that allows it to degrade the leaf material, the cellulosic material in the leaves. So pretty cool to think about the way in which bacteria allow it to degrade a polysaccharide that we can't degrade. So we've now seen highlights of proteins and carbohydrates. We're going to move on to nucleic acids, but first a really quick review. Proteins are made up of what subunit? Amino acids. What are they linked by? Peptide bonds. How about carbohydrates? They're made up of monosaccharides or simple sugars, and they're linked by glycosidic bonds. And in both cases, when those bonds are formed, what molecule is released? Water, right? Okay, good. Take-home messages, getting there. Okay, everybody looks like they're getting a little tired. They're Bridger's yawning, and you're thinking to yourselves, challenge me, Rachel. I mean, really, I know this stuff. Challenge me with something I don't know. And let's see if you can get this one, because this one is a little bit harder. I want you to look at this nucleotide. Nucleotides are the subunits, the sort of building blocks, right, if you will, of DNA and RNA, but they're slightly different, right? These nucleotides are slightly different from DNA to RNA. So what I want to know is when you look at this particular nucleotide, hey, notice there it is, there's that sugar called ribose. There's a phosphate group attached to that ribose at carbon number, what's that? 5, 6? Oh, let's count. 1, 2, 3, 4, 5, right? Carbon 5 has a phosphate on it. And then, hey, look at this. Nitrogenous base attached to carbon number 1. So this is a quintessential nucleotide, but is it a nucleotide of DNA or of RNA? So talk for a minute. I need a drink of water, so you guys talk. Anybody want to take a guess at it? Fill in bold, Jonathan?
RNA.
RNA? Okay, he's saying RNA. Anybody going to argue with him? You going to argue it? Okay, we've got it going on Stan. He's going to argue it over here. Bring it on. Okay. Why do you think RNA? Why do you think?
Yes.
It's a guess. It's totally like, shoot it out there. 50-50 chance. Yeah, why do you think DNA?
Carbon 1 doesn't have a hydroxyl group, so it's deoxy.
You bet. Only let's just change one little thing, because that was really sexy-minded, except for carbon number 2. Right, you got it. Right here, look at carbon number 2. No hydroxyl. So this is deoxyribonucleic acid, right? Deoxy DNA. If it had an OH at this carbon, it would be ribonucleic acid with a hydroxyl. So that's how we differentiate DNA from RNA. Now also, if we had a base right here, what would be one other way we could possibly differentiate? What if the base right there was uracil? We'd be so confused because we'd be like, look at that deoxy O at the 2' and then the uracil. That's weird, right? So we would be real confused. But if we had a U there, we might think RNA. If we had a T there, DNA. Right, good. So the base is one of these characters. So we don't often draw it on there. Sometimes we just call it base because these are kind of complex nitrogenous ring structures. And there are 2 types of these ring structures, 2 types of bases. So we can look at those 2 different types. You guys already argued for the fact that uracil is found in RNA and that thymine is found in DNA. But we should also mention which are purines and which are pyrimidines. Oh, totally got it. She's got it. Okay, purines top, pyrimidines bottom. Okay, anybody gonna argue? Yeah, go ahead, Alex. Pyrimidines on the top, purines on the bottom? You're right. So tell us how you know it. How do you remember?
When I was in high school, I remember the one with the longer name was the smaller one.
Oh, that's good. I know, okay, you want to know how much cheesier mine is than that? Yeah. All good girls are pair. Right? A and G. All good girls are pair. Okay. All right. So whatever, Rachel. Right here, adenine and guanine are the purines. Uracil, cytosine, and thymine are the pyrimidines. But I kind of like Alex's method because then you remember that the purines are the big ones, right? And that helps you remember that they're the double ring structure instead of just the single ring structure. We're not going to do a whole lot of memorizing of the chemistry there, but I just kind of wanted you guys to review and be aware, okay? Phew. So just like it happened that an amino acid bound to another amino acid forming a peptide bond and forming a polymer, and just like one monosaccharide bound to another monosaccharide forming a glycosidic bond and forming a polymer, now we can get the binding of one nucleotide to a second nucleotide forming a polymer. And that's what we're seeing here. So what I want to know now is what in the heck is the name of that bond? And I'm giving you some choices. Is it a beta-O glycosidic bond? Is it a 3', 5' phosphodiester linkage? Is it a 3', 5' phosphoanhydride linkage? Or a beta-N dinucleoside linkage? What do you say, B? Okay. B, we're gathering that it's 3', 5' phosphodiester. Anybody want to argue that? Feel good about it? I think we feel pretty good about that. And if you have kind of a dorky chemistry mind, you will recognize that an ester is a C double bond O. That's an ester. This is a phosphoester because it's a P double bond O. And it's a diester because it's an O bond P double bond O, right? And so you can remember it that way if you'd like, because of its chemistry there. Any questions on that? Does that make sense? Okay, I know. If you don't remember that or you don't have the chemistry background for that, don't worry about it. Just know that it's a 3' 5' phosphodiester bond. Let's write it down because it's a good time to review it all. Proteins, what is their building block? Amino acids. Linked together by peptide bonds. Okay? How about carbs? What is their subunit, their building block? Monosaccharides. Linked together by glycosidic bonds. Good. And if you said glucosidic, you're also right, so don't worry about it. And then lastly, nucleic acids. What are the subunits there? Nucleotides. Good. And they're linked together by phosphodiester bonds, or even more specifically, 3', 5' phosphodiester bonds. Sweet. So this helps us with all of the macromolecules that are polymers of monomers. And then we come to this point where I confuse everything and I say the last macromolecule is not a polymer of monomers. I know, it's depressing. These are what? Lipids, okay? Lipids are cool molecules, but they're not polymers of monomers. They are large molecules, however, and they are pretty darn rad when it comes to their ability to be very highly hydrated. Okay, so let's see what that means, and I have some questions for you, and I also have a pretty sweet picture here that was taken by one of my students on those lipids. Ooh, these are questions on DNA. I'm going to come back to these because we're going to skip them. So, functions of lipids. Energy storage, thermal insulation, surface protection, signaling and recognition, and perhaps there's nothing better than the pad of a polar bear's paw to show us that thermal insulation is a thing. So this was a picture taken by one of my previous students, Marcy Trana. She was up working with polar bears, and obviously this polar bear was not currently conscious. But she was able to get a nice picture of its lipid kind of protection, right? So we see a lot of lipids in here that are allowing the polar bear to keep a kind of fluid nature to its cellular membranes, even in the cold. And that has to do with the lipids that are a part of that, okay? So the lipids are playing a good role in thermal insulation here. We can split lipids into a couple of different categories. I'd like to start with the simplest lipid, and that is the one that is the most maliciously maligned: fat, right? Fat. What is another name for fat? Lipid, yes, but also adipose tissue. Good, I love it. What else? Blubber. Yes. Thanks. You bet. Let's try the technical term of triacyl glycerol. Old school, they used to be called triglycerides. Now triacyl glycerol is the more appropriate term. Let's go ahead and look at the structure of a triacyl glycerol. And what I want you to notice is that it has a glycerol backbone, but attached to it, what are these long chain things called R1, R2, and R3? What are those? Carbons bound to hydrogens, and wait a minute, carbons bound to hydrogens. How do they feel about water? Hate them, right? So lipids are highly anhydrous. That's actually cool because that means that fat is the most efficient storage molecule you can have because it is lightweight and yet it is packed with an immense amount of power. Think about how much a hummingbird celebrates that fact because it's got to migrate long distances and it's got to be really lightweight because it's got to fly at really high speeds, and it loves fat as an efficient storage molecule. So now the question that I have for you guys is, why is this triacylglycerol so dang packed with power? Said another way, why does the blubber have so many calories? Right? So think about it, talk about it for a minute. Why is this so packed with power? And I'll give you a hint, there's some chemistry involved here. Okay, some chemistry involved. No, not in that particular fat. But that's not to say that you wouldn't ever see double bonds in a fat, right? And what's the difference between the two? We call one what? Yeah, good, Lauren. Yeah. Hey, you guys, I got a great question over here. The question that Brent asked was, are there ever any double bonds in these fats? Like, do you ever see any double bonds, or is it always just single bonds? So, do we ever see double bonds in these? Yeah, and what kind of fats have double bonds? Unsaturated versus saturated. These are saturated. Okay, so who's going to put themselves out there and tell me why this is so packed with power? What group came up with an answer? Did you guys? A lot of conversation. But yeah, hit us. You're on today. Yeah. It's Rachel. No. Help me with you. It's Rachel. No, Stephanie. Okay.
It's because they're saturated with hydrogens.
Yeah.
And hydrogens, I mean, they're small, but the more hydrogens there are, the more energy there is in the molecule.
Yeah, good. I love that. The answer that Stephanie has here is a fantastic one. She says, well, they're so saturated with hydrogens, right? And the more bonds that a carbon has to a hydrogen, the more energy it is worth. Now let's put a little more sexy-minded lingo on that, because the more bonds that a carbon has to a hydrogen, the more what? Reduced or oxidized? Reduced, yeah. So the more reduced a molecule is, the more it can be oxidized. That is said another way, the more we can rip and strip high-energy electrons off of it, taking those high-energy electrons to where? The electron transport chain, where we can transfer those electrons from one member to the next member to the next member to the next, and use that energy to do what? Harness as, not yet. What happens before ATP? Sure, ADP is a building block for it, but what is it that we take from those high energy electrons? We pump what? Electrons get transferred, but then we pump protons. Excellent. Okay, so we rip and strip high energy electrons off of fat, and we take those electrons to the electron transport chain. We pump protons, and from those protons, that PMF, that pent up battery-like force that came from the blubber, we use that for what? Now you can say it. ATP, baby, right? That is right. So this is why these are so packed with power, okay? So triacylglycerols, right? Okay, I've got to know. No, more blubber stories, okay. So the other kind of lipid that I'd like to briefly talk about is not a fat, but instead is what is this? It's got a polar head group. Man, that guy's cuddling with water. And then what's going on the other side? Water haters, right? So here's what we have. We have a lovely polar head group and two long fatty acyl side chains, right? This is a phospholipid, right? It has a dual personality. We would say that it is amphipathic. You got it. Because it has one side that loves water, one side that hates water, which means that it is going to form a phospholipid bilayer that is the quintessential core of a membrane, right? And that phospholipid bilayer is going to form, as my old anatomy teacher would draw on the board, like this, right? Oh, that was the day I was hoping he would ask if I wanted to teach the class, and I would say, yeah, I thought you'd never ask. Because this is wrong, right? Why is it so wrong? The tails like to cuddle together because they hate water, and the polar heads, they want to hang out with the water. So instead, the phospholipid bilayer is going to look like this, right? And a phospholipid bilayer is the core unit of a cytoplasmic membrane. And that's where we're going to begin next time when we talk about cell structure, okay? Questions about phospholipids versus triacylglycerols. Is that the only classes of lipids? Are there anything else that fits in there? I hear you. What's other? Yeah, sphingolipids, right? And some sphingolipids are phospholipids. So this is a glycerol phospholipid, but a sphingolipid. So there's more to this. There's actually cholesterol, right? The sterols are also categorized as lipids. So we're hitting just the highlights of some of these lipids here. Now, before you guys get too antsy and you go completely away, I want to do two things, okay? First, I want to note that in a membrane or in a phospholipid bilayer, I use some terminology and some shortcuts that you might get confused about if I didn't tell you what they were. Number one, I talk about two parts of a phospholipid bilayer. I talk about the outer leaflet, and I talk about the inner leaflet, okay? So the outer leaflet is the monolayer that is facing the aqueous exterior. The inner leaflet is the monolayer that faces the interior of the cell. And anytime I draw a picture where I just show a bilayer like that, I won't label the aqueous exterior and the interior. I'll assume you know that the upper one is facing the aqueous exterior, the inner one is facing the interior of the cell, okay? So that being said, I want to briefly run back here to a couple questions we missed on DNA, purposefully because they're easy, and I think they're a great place to start, or a great place to end our day. Okay, in 1953, Watson and Crick, who are the notorious characters who are credited with the discovery of the structure of DNA. Now, what isn't as talked about is the fact that they had snagged Rosalind Franklin's image of a picture of DNA, which totes soups made it a little easier to determine the structure when you had a picture of it. So in any case, Watson and Crick marched into a pub in 1953 and declared that they were badasses. Just like that, Watson is a pompous, arrogant jerk. And they said, no relationship, by the way, and they said, we have determined the structure of DNA. And so let's talk about that structure just briefly. First off, do the strands of DNA run parallel to one another? No? What do they do? Anti-parallel. That's right. In fact, with DNA, we like to show it in shorthand notation, where we have this really simple way of showing the 5' and the 3' ends of the strands, and they run anti-parallel to one another. Okay? Now, wait a minute. What does that whole 5' jazz mean and that whole 3' jazz? What is that related to? The carbon. So remember learning to number the carbons. The 5' carbon is bound to what? What group was sitting on that 5' carbon? the phosphate, right? Now, the 3' is a hydroxyl. So we can see that that anti-parallel structure is typical of DNA. What type of bonds hold the two strands of DNA together? That is, how is the 5' to 3' strand held to the 3' to 5' strand? Hydrogen bonds, okay? So, for example, if the nitrogenous base right here is an A, then it is held together to the opposite strand by hydrogen bonds between an A and a T, right? What about if we had a G, a guanine? It would be bound to a cytosine, right? Assuming that this is DNA, right? So a G and a C and an A and a T. So that is how those are held together, and we know the base pairing rules. You guys just told me that. But because of the base pairing rules, we can always determine what is the complementary strand. So right here we have a 3' to 5' strand written. How could we easily determine what the 5' to 3' strand would be? So what would be the sequence of that strand? What would be first? Yeah? Good. Yeah? Good. Oh, I love ending the hour with chanting. We so just chanted at the end of the hour. So you guys have a fantastic day.